Well, I mean, not live stream, but at least recording.
No, actually we are getting the stream.
You are? Okay.
So there was some internet
I just told
problem.
Jeff it wasn't working.
Yeah, I'm replying to him
good.
actually.
Okay, let's start. Before we continue on with the last bit of last week's lecture, I just want to say one thing. Again, I'm still working my way through your project reports. I've got about 2/3 of them done. So 2/3 of the people in this room, in expectation, should have had a comment for me. If you've had a comment, you will see that I've tried to, address first of all, I should say you've all done a pretty good job of following the pattern of what I expected for this one-page report, which was not much, granted, but you did follow the template that I gave you pretty well, which is good. There are small things here and there that I mentioned. For the most part, I think you did try to sort of read the paper and make an attempt to sort of explain what you can understand and what you need to identify further. Some of you have done a better job than others of identifying where the problems are going to be. And I think that's a very important step. And for those of you who haven't, I've made a point of saying you need to dig deeper and to figure out where you're going to get stuck. Because you are going to get stuck. And I've put a deadline now, I think it's December 18th? Yeah, so that's the deadline for the report. So you've got about a month and a half, which is time, but like with most things, it's compressive. So you'll be surprised how short a month and a half can be when it's only a week. So this is one of those things where you need to put the investment up front now to identify where you're going to get stuck, so that you can come and ask me all kinds of questions about where you're getting stuck. This is not the kind of thing where the TAs may necessarily be able to help. You'll have to come to me to ask these questions. So you need to give yourself time to do that. And again, like I said, some of you have done a fairly good job of identifying these critical choke points in the papers that you're reading. Some of you have not. And trust me, it is surprising to me, but it's very easy to see who actually has read the paper and who has not, in terms of how you read the report. In terms of how the structure of the report is and what people have said about what they want to do in the plan, it is very clear if you actually read the paper or not. Right? Because it's very easy to do something very generic. It's like, oh yes, we must understand the proofs of theorems 1, 2, and 3. Well, yes, but there's surely more to it than that. And so I made those comments in the notes. So take what I've said there very seriously, because the thing I'm trying to do is give you comments that will guide how your final report looks. If your one-page report shows that you haven't really engaged the paper and just essentially cut and paste on the paper, I don't want you to do the final report, because then it'll actually hurt you. If your initial report says that you've really tried to understand the background, then I want to praise you for that, because that's what you should do in the report. Okay? So those comments should be viewed as a strong signal for what I want to see in your final report. And again, I will be providing my own version of the final report, the full 10-page thing. So you will get a chance to see what it looks like. And you will get a chance to adapt your template based on what I wrote. So I don't expect you to write from scratch, but you do have to pay attention to these comments. Okay? You don't want to be cut and pasting. You don't want to be just repeating verbatim what the author says. You don't want to be repeating exactly what they claim. You want to also understand what they claim they do. Some of you have said, okay, this is the paper, and I'm still like, okay, so what is the main result? Why is it important? You don't say that. These are things you need to think about. Okay? So, like I said, many of you already have comments from me. Those you don't worry. By today or tomorrow, they'll be in there. Use those comments, take them apart. If you don't understand, ask me. If you're having trouble with specific concepts, and you went to Wikipedia, and I know many of you go and look at Wikipedia. Wikipedia is great, but it just gives the definition, doesn't give you the real understanding of what a concept is about. And that takes a bit more work. So feel free to post a question. You'll be surprised how many of you have common themes to the work you're doing. So if you post them in the forums, you might get an answer, or you'll definitely get an answer from me, at the very least, right? So, or email me directly, or even come to office hours and ask questions. Although since office hours tends to be often choked by assignment questions, it can be a bit hard to get a word in. But either way, there are many ways to do this. And ask. Don't expect that you have to understand everything in the paper. You don't. I'm not testing you on your ability to understand everything on your own. Okay? I'm testing you on your ability to find a way to understand things, whether it's through asking me or okay? So that's all I want to say now about the project. You have the deadline, so you know when it's due. And I will put up my own version of the report by the beginning of December. So that'll give you at least, good 2-3 weeks more to see what my format is. But I've given a rubric in the project guidelines itself, so that should be enough for you to start with. In any case, right now, your main goal should be to really understand the core concepts, the core methods. And feel free to drop results that you think are extraneous and you can defend and saying, look, I don't want to talk about that, I want to talk about this. That's fine. I'm not expecting you to be able to explain the entire paper. Right? I've said that before. Okay. Any questions before I go on? Okay, good. So I want to continue quickly today with what we left off last time. If you recall, what we were doing was trying to use the abstract notion of LP duality, a notion that was developed to be able to assert statements about, well, given a solution to an LP, is it in fact optimal or not? We argued that if you have an LP, you can syntactically write down this other LP, which we'll call the dual, and the dual, if the primal is a maximization, the dual is a minimization, and in fact they meet. So if you can produce a primal solution that's feasible, a dual solution that's feasible, and their costs are the same, you've guaranteed optimality. And the analogy I was giving to you to think about was max flow and min cut, where we said, okay, I produce a flow, I produce a cut, and they're the same value, therefore they must be optimal. And so what I wanted to do last time was to show you exactly how you might produce the min cut. So I just said, oh, min cut, max flow, they're related. But if you didn't know that, how would you come upon it just by using linear programming? So we wrote down the LP for linear programming, for max flow, which is on the left side. Maximize the total flow coming out of the source. Now, I should warn you, I made a slight modification over the last couple of days to the LP I wrote down last time. And I put both notes up so you can compare the differences. There was a term that's saying minus the flow coming out, so I just dropped that. You don't need that. You just count the flow coming out of the source. Okay? There's a capacity constraint as usual, and there's the conservation constraint, which of course you can write down as two inequalities. It will turn out that you don't need to do that, and we'll see in a second why. And then when we mechanically wrote down the LP, the dual LP, just by doing the transposition, max Cx, Ax less than equal to B, minimize Y transpose B, Y transpose A greater than equal to C, you get that LP on the other side there. Okay? So this is a situation that will often happen, where you'll have a problem, you'll write down a linear program for it, you'll stare at it for a bit, drink some coffee, or not, and then you'll write down the dual, because you can do it mechanically. And then you'll stare at these two things and you'll say, what the heck is going on here? Because what you really want to do is understand the dual not just as a jumble of variables and inequalities, but as something that has some kind of meaning to it. Some kind of more combinatorial or graphical meaning to it. Right? If I look at this LP, it's just a bunch of constraints. If I say, no, this is to solve for max flow and graphs, it becomes much more vibrant, much more picturesque, and I can really understand what's going on. I want to do the same thing on that side. So you have that LP. We already see something that we think is familiar. Minimize sum of CE, YE. Why is this familiar? Well, we know that in the min cut we want to minimize something. We know that involves the capacities. So that seems to be somewhat capturing that quantity. If all the YEs were encoded to be 1 or 0. Right? If the variable YE, which is an unknown variable, is set to either 1 or 0, then that's going to sum up the capacities of all the things we chose to be 1. And so that tells us, okay, some of the Y's are trying to capture the act of picking an edge to be in the cut. Keep that in mind. That's the first observation we're going to make. We don't know what the inequalities mean yet, but we know that first. Okay, so the Y is captured, did I pick this edge to be in the cut or not? And now I have this bunch of inequalities. And here's where you have to sort of stare at things and see patterns. The first pattern you will observe, and in a second I'll explain why that is sort of easy, well, why that is natural, is that remember I had all these different dual variables, the Y's which were for the capacity constraints, and the Z's and the capital U's which were for the two sides of this equality constraint. With a less than equal to, a greater than equal to, and we associated one dual variable with each of these constraints. And I got all those things there. Notice that those variables only occur in the form of Z of some vertex minus U of some vertex. Look at it carefully and see. In the first inequality, you have ZU minus capital UU, you have UV minus ZV. The second one again you have UV minus ZV. The third one again you have ZU minus UV. You never have them separately. They're always together. Well, by the law of conservation of variables. It's a real law. Y have 2 and you have 1. So we'll set DU to be equal to this. Okay, it doesn't change anything. I'm just rewriting the variables. Okay? And then you get something which looks a little bit more compact. It looks like this. I just replaced those quantities by the appropriate B quantity here. So this is just merely a re-expression of the same constraints up there. Geometrically speaking, what have I done? Well, I've reduced my number of variables by, V. I've dropped the dimension of my space by quite a bit. right? Which is a good thing. Notice also that du, so all my z's and u's and y's were greater than or equal to 0. What can I say about du? Can I say it's greater than or equal to 0? Always? Can I say anything about the range of values of du? So I've said du equal to z minus capital U, and those are both greater than 0. That we know from the way we set up the whole dual. But can we say anything about d? Anyone? What can you say about d? You realize this is a trick question. You can't say anything about d. That's the answer. D could be anything. It could be more than 0, it could be less than 0, it could be anything. D is in fact unconstrained. And as a side note, which I won't get into now, the reason D is constrained is because in fact D is, remember I said every constraint in the primal becomes a variable in the dual, every variable in the dual primal becomes a constraint in the dual. This variable du is the variable corresponding to that primal equality constraint. Okay? So a less than equal to constraint gives me a variable that's always more than 0. An equality constraint gives me a variable that's always unconstrained. And if you had a greater than equal to constraint, it would just flip. So you get a variable that's always less than 0. It's a minor technicality. But there's a reason why you can do this trick. You know, if you were looking at this, well, how do I know to do this trick? It's actually because this was an equality. And I made it an equality, put those two variables in, then compact them again. Anyway, so I have these variables here. Can we discern some meaning from this set of constraints that is more organic and graph-like than just a bunch of variables? It turns out we can. And so let me just move up a little bit. Let's take a look at this carefully. Look at that first, again, I've written all the constraints again. yuv plus du minus dv is greater than or equal to 0. I'm going to rewrite this as du plus yuv is greater than or equal to dv. And I'm going to do the same thing for the next one. In each case, I'm going to have d something plus y and edge going from that to the next one is greater than or equal to the value for the next one. Do you recall seeing constraints like this before? I mentioned this earlier, a few lectures ago, when I first talked about linear programming. That constraint up there, yuv plus du is greater than or equal to dv. What might that remind you of? Oh, that's written there, so you know what's reminding you of. When you see constraints like this, you have some label for a vertex, you have some edge, and you have a label for the next vertex, and you have this constraint. Suppose you imagine du to be some kind of distance, and I'm going to put this in quotes because it's not really a distance, but it's a kind of distance. If this were a distance, and that's expressing triangle equality, that's saying the distance to get here plus the distance it takes you to get there can be no more than the distance to get there directly, which is from what triangle equality can be no less than that distance to get there directly, which is what triangle equality tells you. So when you look at those inequalities, this starts to look like some kind of distance. Since you can think of dv as some kind of length of path to v, where the length is measured by this unknown variable y. So that's a weird thing here. It's not like some fixed constant with associated with the graph. You're trying to construct distances in the graph. And there's a very common theme in these kinds of flow problems, that the dual involves building some kind of distance structure. But what distance structure do you want to build? So when you do this construction, it turns out that the label for s should be -1. So the distance to s is -1, which is why I didn't want to say distance. And the distance to t is 0. Again, distance. But then what that constraint is saying, basically, is that if y, sv minus dv, and this thing and so forth, you're starting at -1, you're getting to 0, you're using what are basically shortest path-like constructions. So somewhere along the way, when you add up this distance, you're going to need a 1 somewhere to go from the -1 plus 1 to give you 0. Okay? That's what this is basically saying. Any path from s to t must have 1 in it somewhere. So you can get from -1 to 0. And these are going to be your cut edges. Because basically, if every path from s to t has 1 on it, then if you take away all those 1s, s and t are not disconnected. There is no path from s to t. And so this is giving you the cut formulation of it. So again, this It takes a while to sort of assimilate this kind of concept. But the point that I want you to take away from this, and you can go back home and read this more carefully, is that usually when you have a primal or dual LPs, they're actually telling you something very interesting about the underlying variables they're working with. And one of the interesting parts of doing LP-based reasoning is to sort of figure out what it's saying. If I didn't know what a min cut was, and I only knew what a max flow was, I could, in principle, take the max flow, write the LP, do this, and get the min cut. It would take some effort, but you could do this. And that's the way you can link many problems you otherwise would not know how to solve together. That you write on the LP formulation and somehow they now look similar. And you didn't realize that. Any questions? Okay. So just to wrap up, right? This is what I was talking about. Why do we study linear programming? The reason we study linear programming is manifold. And we're going to see in the next few minutes, we're going to see yet another gigantic application of linear programming. But in the context of flow, so the context of problems where we do know how to solve them, one reason to think about linear programming is to realize that there's this linkage. Oh, actually, let me back up a second. Okay? I want to say one more thing. What I didn't argue yet, at all in fact, is that the values I get are integers. Okay? I just told you that you can interpret this if the y's are 1 or 0, this will work. But suppose the y's are half, then did I pick the edge or not? It's not obvious at all why I should always get 1s and 0s. It turns out to work for max flow by magic. I use Ford Fulkerson, I can argue always get integer values. But there's no reason why it should work. And it turns out you can't prove that you're guaranteed to get integer solution for this problem. It's not obvious at all. But you can prove it. And so that brings me to the point I want to make, that often, if you have a problem you want to solve, you can try to solve it directly, but if you can express it in terms of linear programming, then you have this pair of programs, the primal LP and the dual LP, that give you very deep insights into what makes the problem sort of solution optimal. Very deep insights that otherwise would not be easy to see. That looking at the primal dual LP pairs tells you what an optimal solution looks like. And that gives you usually another combinatorial problem. And so now you know those two problems work in pairs each other, max flow and min flow. Set cover, hitting set. The whole pairs of problems. And that's why we want that tool in our arsenal. We want to have that insight, because having that insight allows us to see connections, to understand properties of optimality. So you've all been doing this assignment approximations, right? And you had to reason about opt. You didn't know how to reason about opt. This is a way to reason about opt. This is a big crank that allows you to think about what the optimal solution must look like, because you have this primal dual LP. Moreover, so that's the bigger picture of one part of the reason why we study linear programming, why they're so ubiquitous in fact, all the machine learning and related things like that. And we'll talk a little bit about going even beyond linear programming to other kinds of constraint systems where you can still do something. And remember, one of the main attractions of linear programming is that you can actually solve it. You can actually take a problem, write it a bunch of constraints, put it into a solver cranks away for a little while, gives you an answer. This is very powerful because now all your work is limited to doing a reduction, to writing down an LP for your problem. You don't actually have to solve it. Someone else knows how to work. In a different incarnation of this class, I would spend some time telling you how to solve linear programming. But that's not for this class. But there are many interesting ways to do it. So again, as a kind of a tool in your tool belt, you want to think about trying to map upon to linear programming, because then you have all these powerful methods to solve. Just like when I said with flows, this is a larger version. Okay. Yes?
So, Ford Fulkerson, I believe, was exponential, the original algorithm. Is it better to solve the linear programming version of
for flows, no. Because for flows, we've seen those two algorithms, the short pipes and the fat pipes, that actually are very combinatorial and work very well. If you take this and throw it into an LP solver, it'll solve it, but in practice it'll not be the best solution. So if you don't know if you write your problems as a linear program, you don't really see any good structure to it, apply it to write a solver. But if something that's where you can actually think hard and write down a clear structure, then in fact you should write down that algorithm itself. And in fact, so there's a whole technique, set of techniques which I won't talk about in this class, but I'll mention. There's a whole set of techniques called that works something like this. Start with an x that's feasible and a y that's infeasible. Okay? So you have a primal solution to your problem that's feasible. I have some flow. There's a way to mechanically construct some kind of y from this that's not feasible, because if it were, you'd be done. Because if you have primal and dual feasible solutions, you have optimality. And then use the feasible x to produce a y prime that's less infeasible. So it's infeasible because it violates some constraints, but maybe it violates fewer constraints than before. Then go back, get a new x, and then go back and get a new y, and so on, till you get both a feasible x and a feasible. Now the insight for how you do these updates comes from the linear programs themselves. So there's a thing called complementary slackness. You can write down a dual constraint, you can say what the primal variables must be, and you can kind of dance back and forth like this. But if you then, again, stare at it carefully and strip out all the linear programming jargon, what you end up with is a very natural combinatorial algorithm. And in fact, you can take the max flow, any of Ford, Fulkerson, and these algorithms and reinterpret them as a primal dual scheme, where you're taking a primal LP, a dual LP, and updating them back and forth. So even though you might say, I want to apply the linear programming philosophy to a problem, if you work enough at it, you can actually then throw it away and end up with a simple algorithm that is inspired by linear programming but doesn't actually have any mention of it. So it's like a catalyst. So it acts on the problem, gives you a solution, but you can push it over. Sometimes you're not so lucky. You really need a linear programming solution to do something, and we'll see that next. But there's this whole category of these primal dual methods, and if you look at, again, going back to data analysis and machine learning, there's a lot of schemes based on taking a primal, taking a dual, and iterating back and forth, back and forth, back and forth. This is a large area of optimization that works like this. So understanding primals and duals is extremely important. Any other questions? The other major application of linear programming is not to solve problems that I know how to solve already, is to solve problems that I don't otherwise know how to solve, to get me something reasonable. And to do that, let me take another example. Let's go back to our favorite problem. Well, my favorite problem. So again, you're given a G, find that covers all edges, and hopefully you know what covering means, that some endpoint of every edge belongs to us. Okay? Suppose we wanted to write a linear program to solve vertex cutout. How would we go about it? I just said linear programming is great, it's awesome, it's full of nice melty chocolate and blah blah blah, but how do we do it now? So first of all, we want to minimize something. So we want to find such that right? Okay. So we want to choose vertices to do something, and we want to minimize the number of choices we make. So like we always do, let's say, so we'll have a variable, xv, which is 1 if x is picked. Okay? So if we encode our problem as xv, which is 1 if x is picked, what would our objective function be? What would be the thing we want to optimize? So we want to minimize this cardinality of the set S.
Sum of the x.
Sorry?
Sum of the x.
We want to minimize now again, should we worry about the fact that I said LPs were a maximization is a minimization? No, because we know how to go back and forth. So let's not worry about those things. It's a linear function, and that's the only important thing. You're minimizing a linear function of the variables. It's linear because you're just adding them, not squaring them. Okay, what are the constraints? I mean, I can minimize this by setting all the xp's to 0, right? But that's not going to work. That gives me an infeasible solution. So what are the constraints? Yeah?
For each edge, I want the sum of the two vertices to equal 1.
Okay, so let's say, so for each edge, so for all e, this is a constraint, that's good. We want the sum of the edges. So let's say for all edge equal to u comma v, we want xu plus xv equal to 1. Now this is a linear constraint, it's a linear function of the variables, so that's good. It's an equality, well, that doesn't matter because we know how to fix that. So this is a valid constraint. And we also want to say that x, and this goes without saying that xv is greater than or equal to 0. Yes?
So why equal? I feel like it should be.
Ask him, don't ask me. This is constraint. Why equal?
You only want the edge to have one vertex.
Is it disallowed to have both? Or is it just bad?
So the reason I say this is because there are graphs where it's impossible to do. So for example, a triangle
Yes.
has 3 edges, you have to pick 2 of the vertices, and by definition, one of them is going to have.
What do you think? So when you said equal to, I want you to pull out your thinking. Why do you say equal to? Because you want to pick one or the other, right?
Yes.
That's what you're thinking. So the sum should be 1. The question is, you don't want to pick, you really would not like to pick both, and as you points out, that you couldn't be made before, so we don't want to. But not wanting to pick both because it's bad is different to saying you are not allowed to pick. When we talk about constraints, we're talking about what's feasible, not what's good. Right? We just want to know what's acceptable. Hopefully the optimization is taking care of the good part. Right? So when you think of your constraints, think about what allows it to be feasible, and don't try to separate out what you want and what's ideal from what's allowed. Okay? So what's allowed here is that you want every edge to be covered. That means at least one endpoint should be picked. The at least will then say this should be, in fact, okay. I have now written down an LP for vertex cover. I can solve linear programming in polynomial time. I have solved vertex cover in polynomial time. Vertex cover is NP complete. I have just shown P is equal to NP. Woo! Or not.
So the problem is.
What? Yes.
Can you explain the inequality?
What does it mean? We are encoding x as like an indicator variable. That's saying it should be 1 if you pick that vertex. This constraint says for every edge, at least one of its endpoints must be picked. Suppose both xu and xv were 0. This inequality would be violated and that edge would be covered. So this inequality is mathematically capturing the statement you must pick at least one point of an edge. Make sense? Okay, good. Any other questions about this? Good, Daniel. Yes, you were saying.
So you're going to say you can't have like half of a connection? You can either have a connection or you can't. So though this technically describes the problem, it won't give you the correct answer because...
It won't?
No.
Because?
Because you either have to choose a connection or you don't.
But we do this for flows, it worked fine.
Yeah, but vertex cover, the edges don't matter.
The edges don't matter.
Well, the weight of the edges don't matter, just where we put them.
You mean, wait, what?
Okay, so
I'm confused about something. I'm not sure you meant putting the edges somewhere.
So vertex cover is defined by we want to have edges so that they, point is,
I think you mean vertices. You want to pick vertices.
Yeah.
Okay.
And so, if we pick some like 0.5, say for a variable, what does that mean?
So let's go back to that example of the triangle. Let's just say our graph was a triangle. What is the optimal vertex cover for this graph? I think we agreed the answer is 2. Right? You need at least 2, you can't make do with 1. Suppose I plug this into my linear program. What is the best solution I can get?
1.5.
You were mouthing it without actually saying it, Scott. So, the claim is 1.5. Why is it 1.5? How do I get 1.5? Sorry? Anyone? How do I get a 1.5 optimal solution for the LP associated with this, the graph, vertex cover on this graph?
0.5 on each vertex.
I will put half on each vertex. Notice that this assignment of x's to the vertices satisfies the constraints. For every edge, in fact, xu plus xv is more than 1. It's great. And now if you add up the xv values, you get 1.5. So something's not right. Even though we wrote an LP that is supposed to capture our vertex cover, the answers we're getting are nonsensical. They don't allow us, what is half? Did I pick it or did I not? Make up your mind. And this goes back to the point that Daniel was making, that in vertex cover, you either have to pick it or not. And you can't just say, well, we'll just let the value tell us what to pick. You need to force the values to be 0 or 1. In fact, this is not a linear constraint anymore. Linear constraints are, inequalities. Remember, you can think of them as lines. You're either on one side or the other. This is not that kind of constraint. In fact, the minute you add this constraint to your problem, you don't get linear programming anymore. You get something called this is called integer programming because unlike linear programming, you have integral constraints on your variables. Okay, instead of just linear constraints. You have linear constraints as well, but you also have these constraints that the answers have to be integers. I didn't have to do this for flow. Somehow it all worked, and there's a mysterious reason why that works out. But it doesn't work here. And once again, the way to understand what's going on here is to look at the geometry of it. So let me draw a picture. So we've argued before that the way to think about linear programming is to imagine you have some kind of region of space. And again, I'm drawing in 2D, but you should imagine it in, I don't know, 13 dimensions or something. Something convenient and easy to do. So, take my class next semester and you'll be thinking in 53 dimensions by the end. So you have some kind of set of constraints, which we've agreed looks like some kind of polyhedral shape, which I'm going to just draw like this. This is my constraint region, the region of x is where my answer is feasible. And we have some notion of a direction. So we want some direction. So we want to optimize along the direction. So, we're going to sort of look for this point here. Okay? This is linear programming. But if I now say I want to do integer programming, something extra gets thrown into the mix. What is the extra thing that gets thrown into the mix? That the only solutions that I view as valid and feasible, in addition to all of these constraints, are integers. all the xi's have to be integer. Which means now, your feasible region actually looks something like this. In other words, I want a solution in that nice polygon, but only at one of the red points. And now what's my optimal solution? It's not that point I circled, because that point on the boundary I circled is not one of the red points. It's not an integer point. Which point is it going to be? It's probably going to be this point right here. Which is not as good. It's not as good a solution. By definition. It's not any better by definition. Let's put that. This problem is integer programming, where you have the constraints which are nice, you have the direction which is fine, but now you can only pick up specific points in your set, the integer points. Does that make sense? And in fact, what we have just shown, just by the previous argument there, we're back to square one. How did I just prove this? I took an NPR problem, vertex cover. I reduced it to integer programming. I said if you can solve integer programming, you can solve vertex cover. I know vertex cover is NP-hard, therefore integer programming is NP-hard. So, all this time we were sort of, luxuriating in the gentle, warm bath of linear programming. And then suddenly this thing comes along and you get spikes of pain coming at you, which is integer programming. And sadly, all our interesting problems, all the NPR problems, are equivalent to integer programming. But all is not, yes?
I was going to ask, are there bounds on how well linear programming can approximate integer programming?
I was just about to get to. All the hope is not lost. Even though we have this integer programming formulation that's annoying and spiky and red, you could just drop the constraint, right? You could drop the constraint of being integer, and you get this slightly larger region. In fact, we can say for sure, we can say for sure that if you are minimizing, like in vertex cover, then the optimal if you're trying to minimize like we're doing with vertex cover and we solve the linear program, the solution we get will always be better than the actual solution because you're minimizing over a larger space. And if you're maximizing, it'll be always bigger, right? Because you have less constraints. And if you look at that picture, that vertex is that a little bit further out. Just enough further out that you can do slightly better. So this is a really good thing. Do you see why this is an excellent thing for us? Remember, I can solve linear programming in problem in time. So what does this mean? What does this mean for approximations?
Approximation. All know the time approximation for FDR problems.
Why?
Because we can solve the linear programming version of it rather than the IP version.
And then what do you do? Does that give you an approximation guarantee? Not quite yet, does it? But it gives you something. What does it give you? What is the thing that I've said we always need? Lower bound. We need a lower bound. Remember I told you that, oh, you think very hard about your problem and figure out some clever lower bound that takes a lot of work? You don't have to anymore. Write your program as an integer program, drop the integer constraints, voila, you have a lower bound. Done. And you can use that to reason, and that's where it gets a little harder, to reason about the actual problem. So this is the other way in which linear programming is extremely powerful. That for problems that are otherwise intractable, that linear programming provides what is called a relaxation. It relaxes the problem. It reduces the number of constraints in a controlled way. It keeps the constraints are the same. It allows you to just go up to the edge instead of stopping at an integer point. And so by understanding the shape of that polytope, you can actually reason about how far away you're going to be and how good your solution is going to be. And by the way, the reason why this works for flows, why you don't have to do these tricks, is because for flows you can prove that all the vertices of that polytope are in fact red points. This is a very surprising fact, but you can prove it. That the constraint system has this particular structure that you're guaranteed all the vertices of that polytope will sit on red points. Therefore, if you just solve a linear program, it automatically gives you a red point for free. You don't get this lucky for most problems. But nevertheless, it shows you how you can reason about the linear program to get some handle on the actual code. Yes?
So why can't, for instance, we say we find a linear programming solution? If we can get like the solution, the parts of the solution, just round everything to an integer, and then voila. Why can't we do that?
Good. If you can prove it. And that's exactly what we're going to do next. So NPR problems are equivalent in a strong sense. They're all NPR to integer programming. And for any NPR problem, you can write down integer programming formulation for it. Might take some problems takes a bit more work than others, but you can do it. Okay. So, for example, let's take another problem. So let's take 3SAT. Instance of 3SAT is you're given a collection of clauses, C1 and C2 up to Cm. Each clause Ci is of the form xi1 or xi2 or xi3 because 3SAT, and each xl is some variable. It's either some variable v or it's not v. Right? So for example, a 3SAT instance could look like v1 or v2 or not v3. That's clause number 1. Clause number 2 could be v3 or not v4 or not v2. That's C1, C2, and so on. Right? And the goal is find an assignment of 0, 1, 2 variables. So I'm gonna modify this ever so slightly. Which you have seen before. Okay? Can we write this in a linear form? So how would we construct a linear programming or integer programming? So the way to think about integer programming is write the linear program and put an integer constraint at the end. Right? So how would we construct a linear programming formulation of max 3SAT? Yeah?
Well, so if we think of every variable being assigned either 0 or 1, then I guess since we're ordering the expression, or since we're ordering the literals, the clauses just have to add up to at least 1.
Right, but we're not trying to satisfy every single clause. We're trying to maximize the number of clauses that we do satisfy. So you're close, you're on the right track, but you need one more bit of encoding. You need some way to encode the idea that did the clause get satisfied or not. How would you do that? So one way to think about this is to say, let's define a variable for a clause as well. Okay, so I have one variable for a clause, we'll call it ci, and we of course have variables for the actual literals in the input. So how might we encode the idea? So if we had a variable per clause, and somehow magically this clause variable was set to, this clause value was set to 1, if it was satisfied or not, what would the objective function be? Maximize the sum of the clause variable. Okay, so let's start with that. So let's start by saying, so let's say ci is 1 if clause ci is satisfied, right? And then we have variable, vj equal to 1 if variable vj is true, right? Okay. So now we want to maximize sum of ci I equal to 1 to m. Okay, what are the constraints now? So okay, I'm going to maximize it by setting all my clause variables to 1. That doesn't make sense, right? So what should I do? How do I put constraints on what those clause variables are? And the point is that there would only be 1 if it is satisfied. We already know how to encode the idea of being satisfied, that the sum of the variable values should be at least 1. So one way to say this is that for each clause, so for each clause cj, right, or ci, let's say, the clause variable itself ci is less than or equal to xi1 plus xi2 plus xi3, right? And I won't go to x's, but I'll fix that in a second. What it's saying is that, if you want to set the clause variable to be 1, at least one of these things must be 1, otherwise you're not allowed to do that. If they're all going to be 0, you better set this to 0. You're not allowed to set it to 1 if they're all going to be 0. So this inequality captures that constraint. It's saying that I want to get the clause variables to be set to 1, but I can't do it directly, so I'm going to do it indirectly as well. Yes?
I thought the variables could be inverted.
They could, that's why I put the x's. The x's, I'm going to explain what the x's are.
Okay.
Yeah, yeah. I'm going to get to that in a second. Yeah, so the x is 1. So for example, xi1 is equal to vj if ci had, if vj belonged to ci, and xi1 is equal to 1 minus vj if not vj belongs to ci. Does that answer your question? Yeah, good catch. Right, so you have to be able to encode the idea of complementing, and that's easy, just do 1 minus that. Right, so for example, for the clause, let's look at one of the clauses we took, which was v1, v2, and not v3. So let's write it out here. So the clause we had was v1 or v2 or not v3, and let's call this clause 1. So the corresponding inequality is going to be c1 is less than equal to v1 plus v2 plus 1 minus v3. Okay? It's linear, so it's fine. Yes? Oh, sorry. Yes, I'm sorry. Thank you. So do you see how I construct a linear expression for each clause? Right? And it is linear. And I can just get a whole stack of them, one for each. So I have a linear program now. And at the end, the constraint is going to be that all the vi should be in 0, 1. So now I have an integer program. And this integer program, you can verify exactly captures max-3 set. Not kind of, sort of, exactly captures it because of this integer constraint. Yes.
Can this kind of construct show why 2SAT is polynomial?
3SAT is not polynomial.
2SAT.
Sorry?
2SAT.
Can this construct show why 2SAT is polynomial? Not obviously. What you would have to do is write, so the question is, okay, so we know that 3SAT and max 3SAT are NP hard. We also know that 2SAT is polynomial, but by the way, max 2SAT is not polynomial. 2SAT is polynomial. Max 2SAT is not. So it doesn't really apply in this setting. But in general, if you had a problem where you want to say, oh look, I wrote down this and it turned out to be polynomial time, you would have to look at the structure of the linear program. In particular, the structure of the constraint matrix. And if that constraint matrix has nice properties, then the problem is polynomial. For example, suppose I have a linear program, maximize Cx, Ax less than equal to B, and the constraint matrix A has the property that every determinant you pick off by taking rows and columns has an absolute value of 1. So it's either +1 or -1, or it could be 0. Then the linear program associated with that has integer solutions. This is called total linear modularity, and that's why flows have integer solutions. That the matrix has this very nice structure. Every subdeterminant has value either 1 or 0 or -1. So, which basically means every entry has to have +1 or 0 or -1, which it actually does. So there are certain situations where you can look at the matrix and read off an answer, okay, this is going to be polynomial. That happens if you're lucky. Okay. So we now have another example of how we can take a NP-hard problem, write it as a linear program, and then throw in integer constraints at the end. And this is a very, very common thing to do when thinking about these problems. And again, the reason is that if I now take this problem, throw away the integer constraints, I get a linear program, which again, in the maximization, is going to give me an upper bound on my optimal solution, from which I hope to build a reason about approximations. Okay. So this is one of the big use cases of LBs for an algorithm design, to get an approximation problem. So what I'm going to do now, if this is all clear, is to go back to vertex cover and show you how you can pull out an approximation algorithm for vertex cover using that formulation. Any questions? Yes. Oh, I see. A dereference question, yes.
I was just wondering, is there an interpretation of this without the 0 and 1 thing, so an interpretation of the linear programming of SAT that is like a question that people care about? Does that make sense?
Yeah, no, it makes perfect sense. I'm just wondering if I have an answer to it. Is there an interpretation of the linear relaxation of reset? I don't know if there's a good interpretation of the linear relaxation. I know there's a good interpretation of the semi-definite relaxation, which is another story altogether, which I don't want to get into right now. But I don't know if there's a natural way to think geometrically about what this polytope does. I have to think about it. It's a good question. Sometimes these polytopes do have a natural meaning to them, and you can say things about them. But I don't know in this case. All right, so let's go back to vertex cover. So in fact, what I'm going to do is I'm going to just grab, I'll just write this down. Okay, so vertex cover LP. Minimize sum of xv to be subject to for all e equal to u comma v. Right? So I want to solve vertex cover. I don't want to solve it, but I don't want to write in a linear program for it. So I write the integer program, throw out the integer constraints, I get the linear program, I solve the linear program. Okay? So let's say my linear programming solution consists of variables, consists of the answers, and we'll just describe it as x star. This is the optimal LP solution. as pointed out, one way you could imagine trying to solve this is to round it. So we'll say our solution to our actual problem, so the xv we want for our integer solution is going to be equal to that notation is what's used for rounding. So it's a floor and a ceiling both. Now this is it's a 0-1 solution. Is it feasible? Can we guarantee that the solution we get is in fact a cover, let alone a best cover? No, you're shaking your head. Do you disagree? You say it's not feasible?
Yes, it is feasible.
So back, you were saying that, yeah, you were shaking your head there.
Yeah.
So you're saying it's not feasible? Sorry?
Yeah, I'm saying it's not.
Ah, but he's saying it is feasible.
It is plus 1.
Sorry?
It should be plus 1.
Plus 1?
It should be
Well, the rounding is basically more than half becomes the next one below
But
half.
we can't flow, you can only say, because it's already minimized. If it make it
Smaller?
yeah, smaller, it can't be visible.
It can't be feasible. So your argument is that if I just did rounding, I might not get a feasible solution. Now you seem to think we'll always get a feasible solution. So can you explain why you think it's always feasible?
Because the two number adds up larger than 1, then at least one of them must be
Ah, you're
more
thinking
than half.
you're 2 steps ahead of me. You're too fast. Okay, we'll get to your answer in about 5 minutes. But hold that thought. As such, as stated here, what you're saying is that if these numbers are, suppose all my xv's, so suppose then my rounding would be terrible, right? Because I would just get nothing at the end. It would not even be feasible. I could say, well, I'm always going to set xv to be equal to the ceiling of xv star. This will guarantee feasibility because the numbers, if you at any value, you will pick it. Okay, so this is you know. So idea 1 has a problem because we don't know what the xv stars could be. Idea 2 gives you a feasible solution. Can we say anything about its approximation guarantee? Okay, so suppose xv star is equal to 1 over 10. Let's just say. What is xv going to be? 1, right? So if xv star is 1 over 10, then xv is going to be 10 times xv star. Right? Yes? And then, so you see what I just did there? If it's 1 over 10, it's going to be 10 times that, right? Okay. Now, suppose we magically knew that all the xv stars, the star means it's from the linear program, were more than 1 over c. So think of this like 1 over 100, 1 over 1000, whatever. Some c is some constant. Let's say we magically knew this. Okay? If this is true, then xv from the ceiling is less than or equal to c times xv star. Correct? Because if all the numbers are at least 1 over 100, then the rounded up value is at most 100 times that. Then sum of xv is less than or equal to c times sum of xv star. But this is my algorithm solution, right? The sum of the actual values. And I'm saying is less than or equal to sum of the optimal solution times of the LP. But we've already said the LP is a lower bound on the optimal solution. I have a C approximation. So you see what we did? Before we used to say, oh, we need some kind of lower bound, come up with a clever lower bound and reason about the algorithm. And I was like, nah, we'll just take the LP and round the answers. That gives us a lower bound for free. And as long as we can make that statement about the LP values, we're good. And of course, now the question is, can we make such a statement? I know it's been 5 minutes, but now you can tell me what you're going to say. Now tell me what your reasoning is.
Saying rounding them will work because the sum of each endpoint in every edge is larger than 1, then at least one of it is more than half.
At least one is more than half. So the claim that you are making,
Or both of them.
okay. So the claim you're making is the following: for all E, okay, equal to U comma V, so this is not what we wanted, by the way. It's not as good as saying that they're all more than half. So in fact, this is not enough. This claim is not enough, even if it's true. I'm not saying it's true yet. Even if it's true, it's not enough to make option 2 work. Okay? But it helps us with option 1. Why? Because option 1, our problem was that we may lose feasibility if all my values were less than half. And if that claim is true, that will not happen. For every edge, at least one of the endpoints will be more than half. When you round it, you will pick a 1, and so every edge will be covered. Okay? So in other words, if this claim is true, if true, then xv equal to the rounded value of xv star works because every edge is covered. Because at least one of the endpoints of that edge will have a value more than half, which will be rounded to 1, so you'll cover that edge. They both might be, that's fine. Remember an example of 3? The optimal solution was half, half, half. That's kind of what we're trying to get at. So why is this true? Why is it true that either of the two must be more than half? Well, it's a pigeonhole principle, right? You're adding two numbers. You're saying the sum has to be more than 1. If the sum of two numbers that's less than 1 has to be more than 1, at least one of them must be more than half. So in fact, this claim is very easy to show. Okay, but where does this leave us? Does this give an approximation guarantee? So now we get round. What should we do? How do we reason about the approximation guarantee we get here? So remember, what we're saying now is that and again we want to compare versus sum of xp star. And we also know that so what do you do? Yep. Not quite yet. Not quite ready.
I just wonder if we can say like the sum of the rounded values is going to be at least the sum of the non-rounded values.
Well, we can say that. So here's what we can say, right? So can we relate xv to xv star? So we can definitely still say this, right? So if xv star is less than or equal to half, then xv is equal to 0. If xv star is more than half, then xv is equal to 1. So we can put these two together and say xv is less than or equal to 2xv star. Right? In the first case it's true. In the second case it's true. Remember what I said earlier? If I can prove something like this, I can't prove that directly, but I can prove the next statement, the then part, that xv is less than or equal to cxv star. That's what I wanted to prove, right? I couldn't prove it directly from that, but I can prove what I need. And so now by summing all these up, given this fact, and we're done. The algorithm is a two approximation. So the algorithm that says, take your graph, express it as a linear program, solve the LP, take the values the LP gives you, and round them. And pick all the vertices whose rounded value is 1. That's your algorithm. So the LP is used as a black box. I just want to put something in and get an answer. I don't care how it's done. But the values that the LP gives me give me a clue as to where my actual solution is going to be. And this is what is called LP rounding. So this idea is called. And there's a large number of approximation algorithms that are designed essentially around this idea. That if you want to solve the if you want to get an approximation, just write down the LP and solve it and round it. This doesn't always work for all problems, but it works for enough problems that's a very powerful tool. Randomize rounding. Toss. And toss a coin with that probability of being 1. So randomized rounding, not for this problem, but for some other problem. Again, xv is equal to 1 with probability xv star. So if xv star is very close to 1, the probability of this being picked as 1 is high and not. And there are problems where this actually works out effectively. You don't want to do rounding, you want to just kind of randomize. So these are the two sort of ways in which, or two of the many ways in which linear programming is a very helpful way to think about a problem. That it gives you this geometric structure, this notion of duality that allows you to relate problems to each other and realize they're actually the same problem to show up in output. It gives you a way to handle hard problems. And again, this is sort of, to repeat myself over and over again, when you start looking at optimizations for data problems, you're invariably solving some kind of intractable problem. And then you write down some optimization version. It could be linear, it could be semi-definite, it could be convex optimization, which is a relaxation. You solve the relaxation and use that relaxation solution to somehow reason about the actual. And the intuition here being that if I have this polytope and I have the edge vertex, there should be some integer point nearby that edge. Not there, but nearby. And the closer it is to the edge, the more accurate my approximation is going to be. The worse my polytope is, if it doesn't somehow capture the integer points, the worse my approximation is going to be. So for some problems, this doesn't get you in. Questions? Yes?
So we said that we cannot approximate general TSP.
Yeah.
If you tried to formulate as a linear program, would it just be an infeasible polytope?
What would happen is that if you try to solve the linear program and get an answer and try to round it, you would get nothing. Or at least we don't know how to get it. In fact, there's a lot of work, TSP in particular, there's been a lot of work on studying sort of it polyhedrally, which means studying different kinds of linear programs you can write for TSP and see what the relaxations give you. So there's a well-known, okay. While this approach to use linear programming to solve approximations is very powerful, it has its limits. It could be that the linear program you've chosen is designed in such a bad way, if you visually think of this, that the integer points are very far from the bound. Right? So suppose by accident you drew this linear program which was kind of skewed in some strange way. Now you didn't do this deliberately, but that's somehow how the constraints ended up looking. And so your integer point was somewhere here, and maybe there was one here and here, but you couldn't fit anything else. Okay? So let's say this is my direction. Okay? This distance here, from what the LP would give you and what the answer is what is called the integrality gap. The gap to being integer. Every LP has one. Before we said, oh, don't worry, you can get close. There's also a limit on how close you can get. You can think of this like saying, if I have my polygon and I have a bunch of integer points in, there is some points that are far, there's at least some distance between the boundary of the polygon and the integer points. There's some minimum distance. That's my integrality gap. No matter how clever you are, if you try to solve that problem using that linear program, you can never get better than that approximation. You will always be limited. So if you choose, so if you have a problem, so if you want to solve, say, TSP, okay, and you think very hard and you write out a linear program for it, this will have some integrality gap, which you cannot beat. Okay? You might come up and think very hard, come up with another LP. This would have another integrality gap, which you cannot beat. So in this manner, you can actually show limitations on this particular line of attack. You can say, look, you came up with this LP. That's great. But here I'm going to show you that there's a gap, that there's a limit beyond which you cannot approximate this problem. For TSP, for example, even the metric TSP, where you can get a 1.5, there's a very well-known linear program that has a 4/3 gap, or it's believed to have a 4/3 gap. We're not quite sure yet. So this is called an integrality gap. LP. Yes?
Since like the actual corner of our LP is not a feasible solution.
Not an integer solution.
It's not an integer solution, so like not an actual answer to the problem. Like, and we get this optimal integer point. Couldn't that optimal integer point be the optimal solution to the problem?
No, it could if you could find it. But often what we're saying is that we're going to reason about the cost of our solution based on what that endpoint is. Right? In other words, the lower bound is bad. In your approximation reasoning, you can't reason any further than that.
Yeah, so you could have a better solution.
You could have a better solution. That's the problem. You just don't know because your LP is kind of shooting you off in the wrong direction. And so there's a lot of skill involved in choosing the right LP for a problem. Because the right linear program for a problem might give you a better approximation than a different one. Like for example here, you might try to add some constraints to your problem to cut it here. If you could do that, now your new LP looks like this. And now you have a hope of doing better. So there's a lot of technology about how to design your LPs and design your constraints carefully to see if you can get a better solution.
It seems like kind of silly though, because like if you do that, like both answers right, you might get the same solution too. Just your gap is different.
Yes, but then that's the point. The gap is the guarantee. What you're basically saying is, oh well, the solution actually was really good. I didn't know it before. Now I do. So it's, I don't know if I'd call it silly. I think it's still giving you extra information. But you're right, the solution itself has not changed in that case. It could happen. Yes?
What kind of assumptions are required to show that you can't do better than an integrality gap?
Produce an example.
Like, I guess in this example, I mean, like with TSP.
What I mean is you produce an example of an input, like a graph.
Okay.
Write on the LP and show that there's a gap.
What kind of gap do you mean? Like it's just
that I will show that if I write on that LP, so like that vertex cover example, right? I wrote on an LP for it, the standard LP. I said, oh, look at this graph. The LP solution is 3/2, but the actual solution is 2. So the integrality gap is 2 divided by 3/2, which is 4/3. That LP is an integrality gap of 4/3.
Is there a way to prove that you have the worst example?
You don't know. So there are cases in which you can show that. There are, so for example, for the traveling salesman problem, you can show now, and this took many years to do this, you can now show that there is no LP of polynomial size that will give you the answer. That doesn't mean it's NP hard. That doesn't mean P is not equal to NP. It means LP-based solutions are not the way to go for that problem. And there's a very interesting story behind that result, but shall keep for another time. But yes, so in very specific cases, you can do this. There's this whole technology of what is called extension complexity that allows you now to reason about the limits on what you can do with linear programming. Yes?
So thinking about duality, for LP we have the dual, which is sort of the optimal for one is the optimal for the other in some sense. It seemed intuitive to me that for integer programming that's not necessarily the case. Is that correct?
There is no notion of a dual for integer programming. What you do is you take the integer program, write its linear program, write the dual, and now you can put integer constraints in the dual, but it's not, you can't really reason about the same way. You always reason through the linear relaxation. Because the way, I mean, how many of you have taken a class in functional analysis? Anyone? So if you are taking a class in functional analysis, when they talk about writing duals, okay, there are 357 different kinds of duals, well, last time I checked. But one way of thinking about duality is that the dual of a vector space is a set of linear functions over that vector space. So the set of linear functions over a vector space is itself a vector space, and it's called a dual. And that's kind of what's going on here. But these are linear functional space, not integer functional space. So that's why notion of duality tend to go through some kind of smooth argument, not through this discrete argument. And that's why it's not. Having said that, there's a notion of a combinatorial dual of a graph which is very discrete. That's a different story. Like I said, there are many different kinds of duals. But this one is important. Any other questions? So I'm not going to do any more detailed sort of focus on linear programming at this point. I basically want to show you what it is, why it's useful, and how it connects to these hard intractable problems. And so when we do have a homework on linear programming related topics, I might ask you, here's a problem like, not like max 3 but somewhere, write down a linear program. Okay, and that's about the extent to which I might ask you. I might say, okay, can you try to round this? I might try to answer that. But there's a whole other area that you can talk about, approximation algorithms and all that. All right? Okay, I'll see you on Thursday. Yes, sir.
So, Ian, I'm trying to find the closest point. So